Perfect. I guess just like a first question for the meeting planning. Dom, are you good to give a demo today, or do you, yeah, okay.
Yeah, I can give a quick demo, yeah.
Excellent, then we'll make sure we leave some time for that. A couple just like quick things to put on folks' radar, and then we can go around the room. The AGU, if you are giving a talk, you have to have 3 slides uploaded by Friday. So I sent around the MT ones, but feel free if you want a second set of eyes to share yours. Am I frozen?
You at least.
Oh, now she's frozen.
Now she's
Big science.
Yeah, well,
so
the
exciting.
leader's gone. Is it like a, is okay.
Wanted to get out. We're going to do some quick reports if you'd like. I can go first on that. After we had a nice, hacking party or coding party basically on Friday. It was fun. It was nice to see people. It's good to get touched up on a few of those things. We almost got the discretized pull request down to 0. Just looking at it. As part of that pull request, I decided to go over the weekend. I implemented a quick, like a faster version of the refined box and refined ball functions, basically. That look for that take a point or draw a ball and then look for every cell that intersects the ball, and then defines around that ball. And the same thing for a box. They're fast for bounding boxes, but it's just nice to be able to use them, as those kind of were a little bit slow in the current and that refined tree function. So now there's like dedicated things, and the calling convention is pretty similar to the insert point one as well. I've also started exercising properties from the discretize library. So it's just a matter of going through and ensuring that it still behaves how we want it to behave. And it'll give us a little bit more control over how the documentation looks and where things are. It's not too much of a problem exercising it properties or exercising it from discretize, because we weren't using it to do too much. So it should be nice. I've almost got that working right now.
Joe, are you gonna segment, because we were talking about basically breaking it apart, right? That single utility. So where do you put your functions, and is it going to be called through that utility, or are we just going to separate them there?
I think we should separate the utility, and it can be called through there. The calling convention is pretty simple as far as those functions. It's like, okay, well, here's an access aligned box. So you give it the 0, 0, 0, and 1, 1, 1, and then at whatever level you want that box to be, and it'll refine it. And you can give it a list of those at the same time. So it can just do a bunch of boxes at once.
Right. So does it make sense then to have it inside that? Because we could just basically take our time and refactor that whole thing and basically get rid of the ball and the box in the current utility and just have that surface. What do you think?
Yeah, I think that's definitely a way to go. For previous stuff, we can have it. We can still have that function around and just have it call the other functions when it needs to, but just point people to the other calling ones soon.
And I guess the only one that we're missing is a line, right? To specify basically points and then refine on an edge basically of a defined by a polygon.
Yeah, it'd be nice to So what we're talking about is having a function that kind of, okay, so in 2D, you would give it 2 points of a line, and it would refine all the cells along that line. And in 3D, you would give it a 3D like a triangular facet in 3D, and would refine everything on that face.
No, but I'm talking that even in 3D, we should have a function. So now we have a point.
Yeah,
we
I mean,
have
you
a
can do a line in
surface.
3D
Yeah.
too. You can do a line in 3D too, but the fundamental thing would be a poly, like a triangular poly.
Oh, I see. And if you give a poly that only has two simplices, then you know it's a line. Yeah, that makes sense. Yeah.
Yeah, so those are just small little things that should be implemented. It's not, the way that this tree mesh works is it's kind of simple. It's just a recursive thing, so it just checks if it, okay, well, if I contain this thing, I'm going to divide. If not, then don't worry about it. And then it checks the cell, and then it checks its children, and it keeps going. Moving on from me, who else does anyone else want to go next before we start calling on people?
Can I ask a quick question, Joe, about the,
Sure.
you were talking about the octree mesh, right? The mesh thing, right? So that is a way of parsimoniously parameterizing the surface model, right? Representing the Earth using far less number of cells. How does that different from Voronoi cell? Because in Monte Carlo, 2D, 3D Monte Carlo method, people use Voronoi a lot.
Yeah. So they're just essentially they're different fundamental structures, like fundamental building blocks, essentially.
Right.
Quad tree is just it's like a semi-structured mesh. Its structure can only be a few things, so it's not as general as like a tetrahedral mesh or a Voronoi mesh.
But it's simpler to implement, right? Because the gradients are still just X, Y, and Z. We don't have to do like diagonal gradients. Gradients are always in Cartesian directions, right?
Okay.
So it's another mesh, essentially. Not like we couldn't implement a tetrahedral mesh, but it's just another fundamentals or another unstructured mesh where the fundamental parts of it are either quadrilaterals or boxes in 3D, right? And it doesn't necessarily mean you understand what a quad, like it's just there's no really, they're just different fundamental parts. The cells are different shapes.
Okay.
Yeah, but I think that Judge, you can basically use the octree or whatever, like quad tree, in the same way they use the Voronoi cells in the MCMC, because the main idea is changing the mesh. So it's rather fixing the mesh and changing the mesh in the inversion process, I guess. So yeah, you could basically use that like different types of mesh, like a quad tree, to do the same types of.
In the octree implementation, are there anything similar to the seeds? Because for Voronoi, we just have a whole bunch of pawns distributed in the 3D space. They are called seeds, and the seeds is simply the center of each unstructured cell. So in octree mesh implementation, I don't know anything about octree mesh. So is there anything similar, or so maybe this is a major difference?
They have cell centers as well. So each cell has a cell center, right?
And if I have cell centers in the octree mesh, is uniquely defined, right?
Cell centers with their associated levels.
Okay.
So that would define like how, like where it is at, and then how big it is.
Okay.
You can think of that refined function as like a seed, right? So you start like you put points, and then you can just refine around that cells, like around that point. So yeah, I think it's just a little bit different sort of tools, but you can actually structure in a similar way, I guess.
There is just a general function where it's like if you give it a list of points, it'll create cells that have those points in them.
Okay. Yeah. Xiaolong, my student Xiaolong is working on Monte Carlo inversion using Monte Carlo inversion 3D gravity using Voronoi. So I was just wondering, since you were talking about Octree mesh, I was just wondering if there's a connection there between Octree or Quadtree and Voronoi. Thank you. Yeah.
Sure thing.
Yeah, I think the Octree should work well in the Monte Carlo method, but for the reversible jump Monte Carlo method, we need to change the dimension of the model space. So in this case, I'm not sure, can we still use the Octree mesh to increase the model cells or decrease the model cell at each iteration?
We could regenerate that mesh, though, right? You could just recreate a new mesh every time. And since the functions are pretty fast, I don't think it would be a big issue, at least not in 2D.
Okay.
Yeah. Xiaodong, keep that in mind. Maybe we can compare these two, Octree and Voronoi, later on down the road.
Yeah. Recreate mesh.
Okay. Devin, I saw you had some stuff on there with your, as a quick report, if you'd like to go.
Yeah, sure. So I've just been pushing really hard at developing the theory section for the Discretize website. I think it's looking pretty good. One of the major accomplishments now is that the theory section and tutorials are sort of happening in parallel. So you can work through you can be going through the theory and then actually running code in a tutorial basically in parallel. So all the things that you're learning about, you can actually go and do with Discretize. They're all connected now. And so now I'm at a point where I'm starting to think about a general implementation of the boundary conditions, because it would be good to have a theory section for boundary conditions and how we're implementing it. And then that's getting me thinking about just a very end user friendly way of putting in Dirichlet, Neumann, or mixed. So that's kind of where my head's at lately. So yeah, I could keep going, or I'm happy to get input from you guys if it's a good time for that. But that's sort of what I'm working on right now.
We're gonna demo it next week.
Yeah, I mean, I guess I could show you guys around what I'm doing. It definitely needs some form of review, but I am going through it quite thoroughly. So I think it's more personal preference details, whether or not we like the titles, some of the layout. But I'm not leaving typos littered through it. So it's fairly developed, but that'd be great. Yeah, I'll do that next week if you guys want.
Devin, you were talking about sort of transferring the docs over to a read the doc type of format. Were you able to do that, or where is that?
Yeah, I mean, right now it's on the branch that I'm working on in the Discretize, and I know we talked about building it and getting it to you in a way that didn't force you to build the website locally. I haven't gotten around to that part yet. So right now I'm working on a branch. I'm building the website locally, and that's sort of where it exists.
You should just be able to send him the your built HTML folder.
That's true. Yeah. Yeah, that's a good point. I could just zip it and then send it over, and then that's actually probably the fastest solution.
Yeah.
Okay, that sounds good.
Yeah.
Because I'm sort of in a position that, I guess by Friday or certainly the weekend, I've got some time to take a look at this. So I'd definitely like to do that.
Sure. So,
what's the scope of like a boundary condition that you would like to sort of implement and like document, or you're kind of like a specific to I don't know, like a DC problem? What's sort of the scope that you're working on?
I would say fully general. I mean, that's the goal of the Discretize package.
Mm-hmm.
And so, as of right now, we have, some of the ways we can implement boundary conditions are, more general for tensor mesh, but can't be done in tree meshes. And if we're making a general finite volume package, we should be able to implement these things. And I also think some of the benefits of doing this is that our implementation of boundary conditions in SimPEG then is actually a lot cleaner. And then we don't have to sort of write this functionality for specific boundary condition implementation for some of the electromagnetic problems. We can then just say, okay, implement this type of boundary condition. Sounds like it comes up in the DC, and then Lindsay mentioned it comes up actually in MT. That could be really powerful because that's a little bit more of a complicated boundary value problem for the 3D problem.
What I'm kind of thinking as far as implementing boundary conditions, and we can have a more detailed talk on this, I don't know, after we go through these group reports, but as we're like implementing them in the different methods, I'd like to keep in mind of what we want out of the package and what would be able to make it more general. So like one of the thoughts I'm having is like, I would like to be able to ask the mesh to give me a list of all boundary faces and their outward normals.
Yeah, which we have.
Like,
I think we would be able to do
like
that.
We kind of have that. Like we're able to infer it based off of the mesh, but we're not able to ask the mesh to like, okay, well, what are all the outward normals?
Yeah, I agree. Yeah.
That way you could like generalize it to other meshes and further on. Future that, but just kind of think about that as you're implementing boundary conditions. Like, well, what would make this easier? What would make this more general?
Yeah, it would just also be, for each, you could either put it in as like a universal thing. You could put in the alpha, beta, and the gamma, whatever your or you would be able to even put one in for each face specifically if you had some kind of function that was defined on the boundary. It would be super useful. And then as that's being developed, it's kind of neat because you could just do the theory section as well. I don't know, I'm pretty happy with it. So I guess I'll show you guys next week, but I'm pretty sure you'll like it.
Anything else?
No, that's basically it.
Okay. Tipo, I see you got some notes on there.
Yeah, so last week I've been working on putting together a tutorial for like joint Grav Mag with Octree and PGI, and doing that was actually like I was reviving like my my other example from prior to simulation, and I realized that the new Mag simulation was making there were some incoherencies in the way it was written with so I've actually incoherencies like especially when you pass a wires to the wires as a mapping. So that's a PR. It doesn't change. It changed like 6 lines of code and change none of the behavior except when you do a joint inversion. So that should be fairly straightforward to review and merge in. And otherwise, yeah, my 3 other PRs still like 2 of them are probably good to go or close to be good to go, and then yeah, there is always a PGI one that's gonna take a longer time. So yeah, and that tutorial that I've been putting together, I will be putting it in probably maybe another PR that I merge in my PGI branch or something like that. But so we can work on that, and maybe Devon, if you're willing to help me for the how to set up the tutorial and like how it's organized that might be useful too. But yeah, so that's kind of the incoming contribution and bug fix that's happening.
Yeah, I mean, there's two avenues that you could add a tutorial or something. There's the examples gallery if you want to keep it just general, and then the tutorials section is, I think it may be a bit more rigorous. There's a bit more of a kind of people learning things in a bit more of an order. So you can kind of decide where you want to put it. But yeah, I can show you around how to do that. There's some syntax for how you need to comment things for it to render properly, but it's pretty straightforward.
Yeah, I have both actually. I have like in my PGI PR, I already have like 2 examples of things that are very simple just to showcase what the PGI is and what's doing. But and the you work with gravity, magnetic, Octremesh, and PGI, and how you make assumption with it. So it's a much longer tutorial. But what my challenge is right now is that having it run very quickly. So like I'm trying to have a mesh that's like 10,000 cells, but still get something meaningful out of it. So that's kind of like where most of my time is getting right now in the design of something that runs quickly and smoothly, but is still meaningful.
Yeah, I think there's a section for that, and I have to go look, but I think there would be a good place for that in SimPEG documentation.
Yeah, the tutorial, that's where I'm putting it.
Cool.
Okay. Anything else?
No, that's about it. So yeah, if you, Joe, or Dom, if you could take a look at maybe at least at the magnetic one soon. I think this one is like very straightforward to bring in, but like yeah, like that was causing me issues when writing that tutorial.
Okay. Yep, I'll take a look at it this afternoon.
Thanks.
So no one else has added to the report, so I can just go around in a circle here on my screen. Peter, how have you been doing?
Good, surviving, thanks.
Okay.
I had a deadline today to submit a revision of a paper, so that kept me mostly busy. I moved everything from Travis to GitHub Actions, so I'm happy. I'm Travis free. I wouldn't have thought I would say that a couple of months ago, but things can change quick. And at the moment, I'm doing all the discretized changes, so I hope to push that to EMG3D in a day or two to be ready.
How did you find the GitHub Actions? Was it easy to transition between the two?
Well, there were different projects, and for the first one, I found it painful, and then it was mostly copy-paste to other packages. Relatively, it's just very fast, I guess, because it's within GitHub itself, which is kind of nice. And then I looked at Leo's repos and copied lots of him. It was a bit of pain with the coveralls, and I saw SimPEG is using CodeCuff, or how you say it, CodeCuff, yeah, I think so. So I first thought of switching, but then it looked like this would be the bigger pain, switching everything. So I stayed with coveralls and found another way to do that. But yeah.
Gotcha.
In the end, yeah, it's one of the things. Now it's fine, and I hope I don't have to touch it, but who knows when we have to move again. So yeah.
Doug, I see you on my screen next. What have you been up to this last week?
Yeah, a couple of things. I mean, I couldn't figure out how to put some pictures into the chat box here. So I ended up putting them in the in our Slack channel. but I guess the things that I'd like to kind of and with the SimPEG codes. And the TKC project has, this is that Kimberlite for those who aren't part of the group in Northern Canada. And it's been a kind of a test bed for us for a lot of different inversions. And in particular, the EM, both frequency and time domain have been inverted. So we wanted to go back and take a look at that. Dom and Sagi, yeah, maybe Mike McMillan were kind of involved in inverting the data with the UBC code and actually got a pretty nice result. So Roman's task was to use a modified code, which looked for the secondary fields and see what we could, problem that has happened, and that is when you have a lot of symmetry in the data acquisition. So you got a coincident source and receiver, and you're just flying along lines. Then if you have a compact conductor, it actually comes out as a ring. So it all has to do with, you know, the symmetry and the sensitivities. But anyway, a compact conductor wants to be a ring. So we're trying to investigate that a little bit more, just to see yesterday of writing an extended email, Sagi, to you, to Dom, and to Dequan, because all three of you, and maybe Mike McMillan also, has addressed this problem at some point in the past. Dequan, in order to kind of get around that, what he did was seed the inversion with a conductor. So you start the model off with a conductive object, and that's our understanding at that point was that was enough to kind of get the vortex currents going. So if you just have a half space, then most of your fields are just resulting from basically galvanic responses, and it's just difficult to get out. You're kind of trapped in that local medium. But if you have a conductor, then now you're going to get vortex currents in there. And then once you launch it off with some vortex currents, then it seemed to kind of go ahead. So that was sort of the end of the state with the HeliSAM data. Now we came back to here, and lo and behold, here's these damn rings again, and they do not want to go away very easily. So I put a couple of images in the in our Slack channel just to kind of show, you know, what they're like. But in both of those cases, I show there, we start off with some kind of a compact conductor, and yeah, you end up with rings. So I'm quite determined that this is the last time I ever want to see this as a problem. We keep addressing this thing, and then it never quite get completed, and then we kind of come back and yeah, we want to do something again. So as I said, I'm writing an extended email, Sagi, to you and to Dom, and also to Dequan, kind of laying out a few things. But there's actually one thing with respect to SimPEG at this point that I'll throw out, and that is some analytic modeling, or at least semi-analytic modeling for, you know, our conductive permeable sphere in a half space. Frankly, if we have one, and we probably should, because I think over the last 25 years, we periodically, every 5 years, decide, oh, we really should have that solution, and let's get it and let's archive it someplace. And all the way back to Greg Oldenburger at the beginning of 2000, we've been doing that. But frankly, I've lost track. I mean, I have no idea where they are. So maybe some of the people here can you know, provide some insight as to our analytic solutions for a for a conductive permeable sphere buried in a half space of variable conductivity and permeability mu. That's one of these things that has use for a whole bunch of things. It would be useful for this TKC data, but it's also useful for unexploded ordnance stuff and just kind of a general workhorse. So I don't know if anybody has got that solution around in a way that could be easily accessed. That would be good. So we got some stuff in free space, but
yeah, exactly. I don't know about an analytic solution or a semi-analytic that is the sphere in a half space. We have the vacuum, this conductive and permeable sphere in a vacuum, which is pretty useful, but I don't know about actually burying it in something and modeling the background and the interaction between the sphere and the background.
I think we should ask what was that? Richard Smith or Andrei Strudinsky. I think Richard may have. They have developed that code. I sort of remember I kind of read a paper about that, but it's a complicated solution. Like you need a lot of integrals. But yeah, we should just ask him first if he has a solution.
Anyway, I'll just throw that out because it is something that I think if, especially on SimPEG, if we're, having people, develop algorithms, just having a few of these base solutions are just incredibly important to kind of tie things down.
Doug, I think this, like the ring thing is really interesting because it's like kind of a fundamental thing, a fundamental reason of how EM works and what it's sensitive to, right?
Yeah.
Kind of really neat that it pops up in the inversions like that too. I mean, I understand that it's frustrating, but it's also really it's neat that it happens like that.
Exactly. I couldn't agree more. And I think this is, perhaps the time now to really investigate this, lay this down once for it would make a really nice paper. I'd really like to see us write something about this whole problem, which kind of perennially comes up, and we understand it, and we have a way of how to proceed.
Well, I think one avenue for, I guess, putting it down in a way where it's reproducible is through the validations section. So this comparison between SimPEG and UBC codes that I've kind of been doing, I think the FEM is, maybe the next one that we want to tackle. And I think that would be a really good space for it. So whatever sort of solution or way of mitigating this that Roman is working on from the UBC end could then be tested, or the results could be shown. And then however we choose to mitigate this problem in SimPEG can then be run. And then we would be able to compare the inversion results from both codes.
Yep.
And I mean, if we like it and we think it has a high enough level of impact, then I'm sure we could adapt it into a paper, and then it's perfectly reproducible in that case.
Anyway, go ahead, Sagi.
From our experience, like frequency domain was less kind of has a less effect than time domain about this ringing effect. So time domain is for sure, like it's always comes up. But frequency domain, from our experience, was a bit less. Because I think the sensitivity function is a little bit different if you actually apply it up. The main thing is this big hole in the center, because you're actually not sensitive right below the loop. But I was actually curious, have you increased just the number of frequency? You got 3 frequency or 4 frequency, but let's say you got, I don't know, 20 frequency. Would it just help? I don't know, just a thought like that.
Yeah, so far we've only just used a couple of frequencies. And yeah, maybe more will help. But I mean, there's just something that's really, I don't want to say simple, but really fundamental here that I think we haven't quite uncovered. I mean, we have this sort of generic idea about kind of the ratio of galvanic to vortex currents, and, you know, kind of done some things, but we haven't nailed it. And I think that would be a nice challenge to do that here.
There's also one important detail that you might be leaving out, Doug, and that's so far with this experiment, we started with just inverting the imaginary component of the data, because we have some pretty significant questions about how we are modeling the real component. The fact that the primary field has such like a higher magnitude than the real component of the secondary field, we're kind of finding that the forward problem is maybe not being solved as accurately as we'd like. The imaginary component seems to be pretty happy, but the real component, when we do the forward modeling, is not showing us what we want, and we have some questions about that. So for now, the inversion that we're testing with the UBC code, we've just kind of been putting in the imaginary component, and I think maybe it might be a bit better constrained if the real component of the data is inverted as well. So I'm not sure if we get as much ring if that happens, but we have to
Pretty sure it doesn't
test
matter.
it first.
In the paper, we had both the real and imaginary, and the rings were coming up.
Okay.
Yeah. Its sensitivity is all sensitivities. You know my opinion about this.
Okay, so if there's nothing else, let's move along. I think we've only got about 20 minutes left or so for the hour. So does anyone else have anything pressing they'd like to discuss? And if not, I'd like to move on to see Dom go through some task information.
Sure, I got maybe one more quick point, and it's the pull request for the DCIP input-output stuff. It's passing all the tests. I think it's basically done. Maybe it needs a final review, but I'd like to know what I can do to get that brought into SimPEG as soon as possible. It is.
So there's still the two parts of that, right? There's the input-output functions that were written, and then also your, like, whatever the fictitious or corrective source.
Right, and then a 3D pseudo section type plotting. Mm-hmm. So really the holdup is just how we want to do this primary, secondary, and whether or not we're happy with it. So maybe it's not as close to completion as I thought, and we could talk about it later.
If you want, you could probably just exercise that part of it, the corrective, primary, whatever part out of it, and then we'd be able to bring it in really quick. If you just want to exercise that part, and then.
All right, I haven't touched it in a little while, so I mean, maybe you and I can come up with a game plan on what we want to bring in and what we want to leave out for now. But there's useful stuff that could be brought in.
Oh yeah, definitely.
Okay.
Does anyone else have anything they'd like to discuss quickly?
One other quick item is the SimPEG governance discussion tomorrow. I put the calendar link in the notes for folks who want to join.
Yep. If nothing else is pressing, Dom, are you ready for a Dask demonstration?
Yeah, I can show you things. Okay, so what I'm gonna show you right now, guys, is the example that's in the it's on that branch. So I have a pull request on. I'm not sure if is it a pull request. I don't think it's a pull request, but we have a branch called sorry for the background. Chantal is like very excited. We have a branch called tiled simulation.
Tiled simulations, yeah.
Somewhere in there. Tiled simulation. So this guy here, and this guy, there's an example under gravity, and it's called plot inf graph tile. This guy here. And so what this example is going to show is how to create, basically how to run an inversion of gravity by splitting a problem into multiple tiles, right? And then this is going to be using all the Dask client stuff under the hood. So the big changes from the current Dask implementation is that I suggest starting using the client. The client, I guess, can see my screen, right? Not yet.
Okay, there you go.
Oh, sorry about that. Okay, now you can see my screen. You good? Yeah.
Yeah.
Okay. Yeah. So the big change now is start using clients, and then with clients we can instantiate workers, which means that let's say you had a big HPC with multiple nodes, and each node has processors. Then you can assign tasks to each of those nodes, and then really like split up your problem into a cluster, basically. Okay, so what I'm doing in this script here.
John, would you mind just making that a little bit bigger?
Yeah, I can definitely do that.
Thank you.
Hold on. I'll change my font in this. Hang on, I'm not too sure how to do it in PyCharm.
No problem. If it is a problem, that's fine. It is big enough. But
yeah, no, I don't have.
Yeah, I would guess it'd be under the view tab.
Appearance. Sorry, it's gonna take too much time. Let's just go on. I'll figure out the next slide.
That's fine. I'll move closer.
Yeah. Okay, so this is a script. So I'm instantiating a client on top of my script. So I'm basically telling my computer right now it's going to be a local cluster, right? Because I don't have multiple machines. So it will look at it as it was a cluster of a single computer with 12 threads. Okay. And then right now I don't have any workers, so I'm just going to give it nones to all my problems. I'm just going to give it none. So it will basically, when the client receives a worker called none, it just distributes the work to all the threads. That's just how it works by default. So first we need to basically create tiles, right? So basically take the survey, split it into chunks, and then create meshes for each one of them. And then for each of those simulations, we're going to have a local misfit. And then the local misfit knows how to project itself back to the global mesh. So this is a delayed, I just put a delayed decorator on this so that we can launch all those mesh creation in parallel. Okay, so the first part is pretty boring. It's just creating a synthetic survey, right? Some topography, I created a global mesh just to simulate the data initially. That's totally not interesting. Keep going. Yeah, so here I'm just simulating some data, and after this, it's this part is kind of ignored. Yeah.
Can you explain a little bit more, like what information are you passing to the workers and where the computation is happening under the hood?
Yeah, absolutely.
So it's very high level at this point, but yeah, it's like
I'll go down. Yeah, absolutely. It's like I'll go down the details. Yeah. Okay, so this for loop here is basically just you see we added a function called tiled location. So you given XYZs and how many tiles you want to do it, and it's going to use a k-means to just segment it basically into a number of groups. So here this function is requiring a list of XYZ, a list of indices for a list of indices for each of the tiles. Okay, and then I'm just feeding this into the delay function here. Back on top, and then this function is going to create, from this list of locations and hubs, it's going to create a local mesh and then a local misfit. And I'm going to spit out a local misfit. Okay. Now the neat thing with the client, and then I'm going to go back to it, is that I can run this loop, but I don't need to wait for the tiling creation to be over. I can just keep going, right? And I'm just appending to the client tasks, basically. So I'm going to call my client and I'm going to say, compute this delay function here, and then append this to a list. And what this returns, what this part returns here is a future. And basically it's just going to be running in the background. So I'll just run this right now. I'm in debug mode. So it's going to be pretty slow, but it will run. Hang on. I'll just run this in debug mode. I have the, hang on, I'm stuck here. Start up. One sec, sorry guys. It's just somehow PyCharm is having trouble. Wow, sorry about that. Something's really wrong happening here. Okay, forward, it's going to run the forward calculation. The thing is that the client and the running it in debug mode is not it's not super friendly. Why isn't it letting me skip? Well, I think we'll have to reconvene because my whole IDE is crashing on me.
I think it's probably okay. You don't have to.
Yeah. Okay. Yeah. Sounds good. I'll just show you the code. Yeah. I'll show you internally then. Yeah. That's a good point.
One question there. So now you got it hasn't run yet, right? Like that local data misfit function hasn't generated yet, but you had a delay function that will generate, that will do that computation later, right?
As soon as you call, will fire off the calculation on the worker, right? So if you do a cut address, well, my thing is like really big. Oh shoot, that's why my keyboard was off. I'm sorry. Okay, so if you put a worker here, the client will launch a calculation on a specific worker IP address. So this would be an IP address of a worker, right? 192.03.4 or something, right? This would launch calculations on the worker. Yeah.
So it starts the calculation, but it doesn't need to finish for that operation to return a value.
Correct. So here I will be able to do it because now my keyboard works. So this is doing nothing, right? You're just creating the delay function. And now if I launch this guy here, I'll show you what happens. If I put this here, so I have a delay function, and if I do this, you see it returns a future. And the future right now, it's telling you the status that it's pending, all right? But if I do a client that gather on this, it will wait for the calculation to be over, and then it will return the result. Right, and now it returned a misfit function. So it fired off the calculation as soon as it was over. It returned me the result of the delay function, which in this case is a misfit function. Does that make sense?
So one curiosity that what I'm still struggling to understand is, so you got a global mesh and a local mesh, and you need some sort of mapping function, and you need some under-level calculation that you need to, let's say, generating the sensitivity for a local mesh. Where that's actually happening, is that on the worker side or on the parent? So what I'm curious about, where that computation is happening and what are you passing to?
Yeah, that's right. So the calculation is happening on a misfit. So the misfit knows about the worker that you want to assign to a specific local mesh. Right. So then when we go to the actual inversions or the sensitivities, I'm just going to show, I'm going to go down to it because it's taking too much time. Let's go to the inverse problem. Okay. And in inverse problem, we have the get fields and the eval function, right? The eval function is the big one. That's where we're getting the gradients and the Hessian and the fields for each of the misfits, right? So when we ask for a get fields, it goes in here, and then it cycles through all the misfit functions, right? Because it's a combo misfit at this point. And then for each of these guys, again, it's gonna fire off basically the calculations of the fields for that misfit, and then it's going to use the workers. It's going to use its worker. Right. So the main inversion, the main branch, only holds basically a bunch of small misfit functions, and then ask to execute each one of them to execute its own field, its own gradients, and its own Hessians, and it's just going to collect the result at the end.
Right. So for instance, let's say you got a global mesh and then a lot of local mesh. Okay.
Yeah.
And that local mesh information is stored in the simulation, like that local data misfit object. So that's the container, and you are passing that into a worker. Is that the idea? So it's like somehow they pickle that and then pass it into a worker. Is that how it works?
Yeah, so that's a good point, man. Because currently I only looked at the PF, right, and the sensitivities would be stored on the worker, on the worker's memory or like drive. And that's something that we still need to test, is that we need to make sure that we're not moving the mesh, or we're not moving the sensitivities between the global and the local worker, because that's too much passing stuff on the network. Yeah. So basically, the worker will need to hold the stuff. The simulation parts will need to hold it there.
Another question, Dom, is are you tiling for every receiver location, or are you tiling for little groups, or can you do both?
That's what you can decide to do. It doesn't really matter, right? So here in this case, I'm creating simulations that are just patches of receivers, but that just depends how you want to define your misfit, right? If you want to define your misfit in terms of frequencies, you just create simulations, one for each frequency, and then you just append a bunch of simulations, a bunch of misfits. It's really up to you. It doesn't matter, right?
Okay, so yeah, really, you're just each chunk of information that you want to have is its own simulation, whether or not you're partitioning it by frequency or clusters of locations.
Exactly.
It's a mini simulation. It's a tile simulation, and each one will have its. Okay, no, that makes sense. That's good.
So it's pretty open to what you want to do. After this, it's all mechanics of collecting misfits from all this whatever stack of simulations that you created. Okay, and then back to the inverse problem. So when we evaluate the function, so it's gonna do this for the fields, right? It's gonna ask all the workers to calculate fields, collect the result, and then for the gradients, it's the same thing, right? It's basically here just asking the global misfit, its derivative, and then we have a Dask data misfit, and the Dask data misfit just it's going to cycle through all the local and then ask for its own derivatives. And then at the end, it just collects it all. I guess it's on the objective function side, right? Because all of these guys are just objective functions. So if you call it, then it's going to ask for fields, and it's going to sum up or like append all the fields together. And if it's for derivative, then it's going to, ask for all the sub problems to submit their own. And then for the Hessian, or like the deriv2, then it's going to send the vector to all the workers, compute it, and then just sum them all up at the end. So you guys can go through the code. And I think the outstanding questions, as you said, Sug, is we need to make sure that that workers, that the simulations are basically stored onto the worker and not sent back and forth between the domain, between the client and the workers, basically.
That's actually where sort of I'm still having, like, I'm struggling to kind of understand. So you need some place to that be stored, right? So that that local misfit class need to be stored at some point, like at some place. Like, I guess that's actually not on the workers, but on the parent. Because on the worker, let's say you got 10 nodes or 10 workers, 10 processors, but you got like 100 meshes. So you cannot actually you cannot always store them. So I think that process in the worker is sort of on the fly. So you always need to pass information from the parent that needs to be stored. And then that can be evaluated on the processor or worker side. So yeah. That was my question. And the one other thing that I was curious that suppose you got pretty big mesh, big global mesh, then that projection function, you need to project, right? You got a local mesh, your local sensitivity that you calculated, and then you need to project or surject that back to a global mesh. So that projection function could be pretty large, right? Like in terms of, even though it's a sparse matrix, it could be large. And I was actually curious where that is stored. Is that, where do you actually store that P matrix?
Yeah, like, currently it's going to be a client. It's going to be your local, your main node that's going to, currently that is holding them all. Yeah.
I see. Got it.
Because I mean, you can broadcast vectors to your workers, but still at the end of the day, it's going to be your main node that's going to have to, yeah. Because when you think about it, when you're building your misfit functions, you're appending them all as a list, and then your main node, when it has the global misfit, it technically holds everything inside, right? So the main node would have it all. So we would need to change the way we're basically storing things in the
store
the potential fields. It's pretty easy because we're doing a to ZAR and a from ZAR. And then the hope is that since the calculation is done on a worker, the to ZAR will be stored locally where the worker is, right on the drive of the worker. And then after the from ZAR, it's the same place. So in theory, if we store sensitivities, then it's not an issue because we can store things locally.
Right.
We obviously need to double check this with a real like distributed system to make sure, and that's what John is gonna experiment on because he has one, to be able to make sure that when we're doing a from and to ZAR, that the ZAR stays on the worker or on the node. Let's call it the node.
Hey Dom, a real quick question about the sensitivity. So I don't know how. So how is the sensitivity calculated? Is it calculated at each small region or?
Yeah, that's correct. Yeah, so each small region has its own little sensitivity. Yeah, that's right. So the simulation, right? Basically, we're parsing patches of data, and then each patch of data has its own sensitivities, and at the end, it's just a projection from the local sensitivities to the global sensitivity, okay, which is just a vector expanded, right? It's a short vector, and then we expand it to the global vector.
And is there any parallelization happening for the sensitivity calculation for each small region, or?
Yeah, absolutely. Yeah. So right now you see I'm pre-computed them in that example. So I'm just doing a for loop. Right. So I'm creating all my problems in a for loop, and after this here, I'm just triggering right away the to ZAR for the sensitivity calculations all in parallel. And maybe I can run this line. So I'm just gonna run to here, and you'll see what happens. You'll be
parallelized over the data points, right? Oh.
Parallelized over the data points and over the tiles, right? So it's two levels of parallelization. I'll show you the work. Okay, so I created my tiles here, and now I'm gonna start spinning the sensitivities. But at the same thing, because it's a client, I don't need to wait for it to be over. So I'm just gonna show you how it looks real quick. Okay, so this is my task scheduler. So I'm gonna, I have 4 tiles, so I'm gonna fire up 4 sensitivity calculations at the same time, but I'm not gonna wait, right? So here I fire the first one, and then you should be able to see the task go on. Oh, I guess I already calculated it. 1 second, I need to kill my old sensitivities. My bad. All right, I'm gonna remove that break here, start over. 1 second, guys. That would work or nothing. Okay. Bear with me. It's good to have a keyboard that works. I was starting to freak out here. Why is there nothing going on?
Live demo is never easy.
I was cleaning it, and then I forgot to turn it back on. Okay. All right, so I'm gonna fire up 4 sensitivities. I'm just gonna refresh my kernel here. Okay. So first sensitivity is gonna kick in. All right, so it started calculating already. All right, but I'm not gonna wait. I'm gonna fire the second one, and I'm not gonna wait. I'm gonna fire the fourth one, the third and fourth one. All right, so in the background, it's just sending all the, it's computing all my parallel to this on top of this. Now I'm firing up all my tiles back to back, so my scheduler is full. Does that make sense, Jojo? Am I saying nonsense here?
Yeah. Yes, thank you.
And what's important is that you don't want to have a white gap, right? When you look at your tasks, you don't want to have downtime. Here I have the downtime because I paused it, but if you zoom into your calculations, you want to have solid blocks. That means that this was evaluating integrals the whole time, and then there's some concatenating vectors and all that stuff in between. But I have very little downtime, and that's kind of what you're looking for to make sure you're fully parallelized. And then just quick comment, just to finish here, because we're already past the hour, but there was some inefficiency that we're doing in the optimization, and I think it would be nice that we just generally try to fix those. If you look at the inverse problem, one thing that's starting to take me a lot of time was the regularizations. Like we were for looping over multiple objective functions multiple times and doing a ton of even if it's sparse matrix vector, it still takes time. So I would recommend that we should just form the regularization. It's a sparse matrix, right? You just form it, and then every time we ask for J and the Hessian, we just do one matrix vector product. It's a lot faster than having to loop and to do to repeat the same operations over and over again. So that was a nice speed up. And then what about it? Yeah, that's about it.
But then, for, let's say, for your LP inversion, your regularization function changes through iterations. So
yeah, but this is reformed at the beginning of the iteration, right? So once it's formed, it's done.
Oh, I see.
Yeah,
I see. So So for every iteration, we're going to update that, but within the iteration, we just store it and
exactly.
Yeah.
There's no point, right, of each Gauss-Newton cycle, so we can just keep it.
Iteration, we think we're all only evaluating the fields once, but a dpred, for instance, it's evaluated a lot of times. So whenever we're writing the code in SimPEG, you make sure there are a lot of function evaluations, so make sure remove all the repetitive calculation.
Absolutely.
That's not required.
Yeah. Optimization, you see, I kind of rework the Gauss-Newton iterations, but really the big chunk here is just the Hessian call, right? And then we only need to do it once. So yeah, basically there's not much changing here. I was just double checking that everything was done properly, but yeah, that's about it. So obviously there's a lot of details. It's going to require a lot of reviews from everyone, but I think it's moving along. I have a little graph that can show you the quickly the scale up, right? I ran this problem over problem sizes, so from like a 0.5 gig problem to a 50 gig problem, and then over a number of tiles, and you see that we're at some point, if you keep tiling, you're increasing the overall runtime and sensitivity time, just because the overhead of creating meshes and looping and all this. But for very large problems, you can have almost a factor 10 of runtimes improvement as you increase the number of tiles. And it looks like this new client thing really scales up quite nicely. So it's quite promising.
This is really exciting.
Dominic,
Thanks for sharing.
I was just going to bring in one comment. That looks really nice. I'm wondering if you or any of the group has really been interacting at all with Dequan. I mean, a lot of these things were kind of at the heart of his thesis. I know when he went back to China, he was planning to continue on some of these. He's perhaps a little bit more involved with machine learning. But it seems that this might be a problem that would really resonate with him, and he may have some valuable thoughts or input. And also it might be something that he could really kind of connect with and perhaps get the Chinese community or the people that he's been working with kind of involved with the project and a bit more with SimPEG. I think there's some benefits there. So I don't know whether anybody has been in touch with Dequan recently. He initially was enthusiastic, but he's kind of dropped off a little bit off of the radar.
Yeah, totally, Doug. I totally agree. I think where Dequan's going to want to come in is how we do the tiling, because that's what's its focus, right? Right now, at this point, we're just laying down the infrastructure on how the parallelization is done over the tiles. So it's very unrelated to geophysics at this point. But yeah, we should bring him back in the fall for sure once we have something more solid running. Yeah.
Good.
Dom, I got a quick question about the sensitivity runtime.
Yeah.
So why let's say you got a big problem and now you're increasing the number of tiles. Why the sensitivity calculation for large problem increasing with increasing number of tiles?
Yeah, so there's a sweet spot where okay, so every time you tile it, you basically reduce the overall sensitivity space, right? But then it's a summation over mesh creation, and then what else is going on here? You need to do the tiling on top of it. So eventually your overhead of creating tiles is gonna start to take over. And eventually also, eventually you're gonna get a saturation, right? Even if you break down the problem down to a single point, you still need to currently to mesh out to the global mesh, right? So eventually you're not gonna be saving too much by breaking down your problem further, because you still need to create like tons of meshes, basically. Yeah.
Oh, I see.
There's a saturation, there's a sweet spot where eventually tiling more is Come again, Joe? What you said? Yeah, absolutely. And here on top of this, there's the other issue of the SSD drive, as you said, right? It's a hardware thing where I'm limited eventually by the speed at which I can transfer stuff from memory to SSD. So there's a tons of factors that influences the runtime. It's really hard to predict. Yeah.
Gotcha. But great. That's exciting.
That's it.
Yeah, well, thanks for showing, Don. And
Yeah,
for sure,
apologies for the kerfuffle, but it's getting there.
Woggy is clapping.
What's
Just-
that?
Oh, just me. The little clap icon
Okay.
shows up on people's faces. Okay, well, if there's no any other pressing things to discuss, I think we're good. We'll see some of you guys tomorrow for the discussion, the governance discussion, number 10 a.m. Pacific time tomorrow. If not, we'll see you all next week. Have a good week.
Have a good week, guys.
Cheers, guys.
Thanks, everyone. Thanks, Tom.